Here we are, stepping softly into the cosmos, where ancient mysteries unfold not with fanfare, but with the gentlest whisper of light. Tonight's companion is a star that asks nothing of you except perhaps your curiosity, and maybe, if you're willing, a slow unraveling of the day's noise into something quieter. This isn't the kind of celestial object that demands attention, flashing its brilliance across the heavens like some cosmic billboard. No, this one hides in plain sight, modest and unassuming, tucked into a corner of the sky most eyes will pass over without pause. Its name, HD 140283, sounds more like a reference number from an old government filing cabinet than the title of something profound. You'd be forgiven for thinking it belongs on a license plate rather than in the annals of cosmic history. Yet this unassuming flicker carries a secret so staggering that astronomers have paused mid-equation, double-checked their instruments, and quietly asked themselves if they've stumbled onto something impossible. The secret is time itself, stretched so thin and long that it almost brushes against the very beginning of everything. The star earned a nickname that feels far more fitting than its catalog designation, a name borrowed from ancient lore where longevity is legend. Methuselah, they call it, after a figure said to have lived nearly a millennium in stories passed down through generations. It's a name that immediately conjures images of endurance, of something that has simply refused to stop existing through eons of change. And that's exactly what makes this distant point of light so captivating to those who study the heavens. Methuselah isn't famous because it's about to explode in a supernova, showering the galaxy with its remains. It's not famous because it's swallowing planets or wrapped in glowing clouds of gas and dust. It's famous for a reason that sounds almost absurdly simple. It's old. Breathtakingly old, perhaps older than anything else we've ever found still burning. Before we venture further into this story, let me ask you something gentle, something to ground us both in this moment. Where are you right now, as you listen to these words drift through the space between us? Is it late evening where you are? The kind of hour when the world finally loosens its grip and allows you to breathe? Perhaps it's the middle of the night, one of those wakeful hours when sleep has temporarily abandoned you and you've turned to the universe for company. Or maybe you're in the early morning, that strange liminal time when yesterday hasn't quite released you and tomorrow hasn't fully arrived. Wherever and whenever you are, you're here now, and that's enough. Tonight we're not just talking about a star burning in the constellation Libra, barely visible even under the darkest skies. We're talking about time itself, measured not in the ticking seconds of your bedside clock or the minutes until your next obligation. This is time on an entirely different scale, time measured in the slow conversion of hydrogen into helium, in the gradual enrichment of galaxies, in the patient accumulation of heavy elements across billions upon billions of years. If this kind of gentle cosmic wandering brings you some measure of peace, if it offers your mind a place to rest after whatever the day has demanded of you, then perhaps you might consider giving this video a small gesture of support. A like, a subscription, whatever feels right to you in this moment. There's no pressure, of course, no urgency. After all, our subject tonight has been waiting for over 13 billion years, so it certainly understands patience. Now, let your shoulders drop just a little bit more. Let whatever tension you've been carrying begin to dissolve into the background like stars fading into dawn. We're about to follow a beam of starlight that has traveled across the vast emptiness between that ancient survivor and our small blue world. The distance isn't particularly far by the standards of the galaxy, only about 200 light-years away, which in astronomical terms is practically next door. It's not quite a neighbor dropping by to borrow sugar, but it's close enough that we might imagine seeing their porch light from our own cosmic doorstep. Yet even though Methuselah is nearby in the spatial sense, it's impossibly distant in the temporal one. This star belongs to a generation that witnessed the Milky Way when our galaxy was still figuring out what it wanted to be. It formed when the universe had barely begun to develop the chemical complexity that would later give rise to planets, oceans, mountains, forests, and people lying in bed wondering about their place in the cosmos. To understand why this matters, you need to know that not all stars are born from the same ingredients, that the universe has something like a recipe that's been revised and enriched over time. The first stars that ever existed were made almost entirely from hydrogen and helium, the simplest elements left over from the Big Bang's primordial furnace. They had virtually no carbon, no oxygen, no iron, no calcium, none of the heavier elements that make rocky worlds and living bodies possible. Those more complex ingredients had to be cooked inside stars first, then scattered into space when massive stars reached the end of their brief, violent lives. Each subsequent generation of stars inherited a richer mixture, gas clouds seasoned by the deaths of their predecessors. When astronomers look at a star and measure very little iron compared to the sun, they're not just noting a chemical difference. They're reading a birth certificate written in the wavelengths of light, a document that reveals when and where that star came into being. Methuselah has remarkably little iron relative to our sun, and that single fact tells us it formed extraordinarily early, before the galaxy had gone through many cycles of stellar birth and death. Imagine, if you will, making soup at the very start, before anyone has added the herbs or salt or vegetables or spices. The first cosmic gas was like that, plain and simple, mostly just hydrogen and helium with barely a trace of anything else. Over time, as stars lived out their lives and died, the universe became increasingly complex and interesting. It gained carbon for building molecules, oxygen for water, silicon for rocks, iron for planetary cores, and eventually all the intricate ingredients needed for dust, moons, atmospheres, and curious humans pondering the age of distant stars. Methuselah comes from a time when that cosmic pantry was still nearly bare, when the recipe had only just begun to develop its depth and character. That fact alone would make it interesting to the astronomers who dedicate their lives to understanding stellar evolution. But the real drama, the moment that elevated this modest star from scientific curiosity to cosmic celebrity, came when scientists tried to pin down its age with precision. At one point, the numbers suggested something that sounded like a logical impossibility, a paradox that made even the calmest researchers pause and furrow their brows. The estimates indicated that Methuselah might actually be older than the universe itself. Now that's the kind of statement that makes even the most patient astronomer sit up a little straighter in their chair. A star older than the universe is like discovering a person older than their own parents, or finding a building constructed before the ground it stands on existed. It doesn't necessarily mean the universe is broken or that our understanding of physics is fundamentally flawed, but it does mean something needs closer examination. It means the measurements are delicate, the uncertainties are real, and nature is very good at reminding us not to become too confident in our conclusions. The universe, according to our best modern cosmology, is approximately 13.8 billion years old. Methuselah's age, at least in some early estimates, came out to around 14 billion years, a figure that seemed to violate the basic rule that nothing inside the universe can predate the universe itself. But here's the crucial detail that keeps this from being a true paradox. That age estimate came with uncertainty, with what scientists call error bars. If someone tells you a bus arrives at 6 o'clock, plus or minus 15 minutes, you don't accuse the transportation system of breaking the laws of time if the bus shows up at 5:50. Astronomy works much the same way, except instead of a bus schedule, we're dealing with ancient stars, and instead of 15 minutes, the uncertainty might span hundreds of millions of years. As scientists refined their measurements of Methuselah's distance, brightness, temperature, and chemical composition, the apparent paradox began to soften and resolve. The star wasn't truly older than the universe, it turns out. It was simply very, very old, close enough to the cosmic beginning that the numbers came tantalizingly close to the edge. And that's one of the beautiful things about this story. It doesn't end with a simple trick or an embarrassing mistake. Instead, it opens a window into how science actually functions in practice. Measurements improve gradually over time, uncertainties shrink as instruments get better, ideas get tested against new observations, and strange results are neither discarded because they're inconvenient, nor accepted blindly because they're exciting. They're examined carefully, patiently, sometimes over the course of years or even decades. Science at its best isn't someone standing on a mountain declaring they have all the answers. It's more like a room full of thoughtful people quietly saying to each other, "Let's check that one more time, just to be sure." The question of how far away something truly is becomes surprisingly important when that something is a star holding clues to the beginning of time itself. Distance in astronomy isn't just a matter of satisfying curiosity about cosmic geography or filling in numbers on a celestial map with precision. It's the key that unlocks nearly everything else we might want to know about a star, including how bright it really is, how it compares to others, and ultimately how long it's been burning in the darkness. Without an accurate measurement of distance, we're left guessing about the star's true nature, like trying to judge someone's height from a photograph taken at an unknown angle. Methuselah sits roughly 190 light-years from Earth, a distance that sounds enormous until you remember the Milky Way stretches across 100,000 light-years. In galactic terms, this ancient star is practically in our neighborhood, close enough that modern instruments can study it with remarkable precision and detail. A light year, despite how the name might sound to someone hearing it for the first time, isn't a measurement of time at all. It's a unit of distance, specifically the distance that light travels in 1 year while moving at its constant, unwavering speed through empty space. Light moves fast, almost incomprehensibly fast, covering about 300,000 kilometers every single second without ever slowing down or taking a break. To put that in perspective, light could circle the entire Earth more than 7 times in just 1 second if it felt inclined to sightseeing. Over the course of a year, all that relentless motion adds up to a distance so vast it makes human-scale journeys look absurdly tiny. When we say Methuselah is 190 light-years away, we're saying its light has been traveling toward us for nearly 2 centuries now. The light entering our telescopes tonight, the photons that carry information about this ancient star's temperature and composition and age, began their journey long ago. They left Methuselah's surface around the time people on Earth were living in a very different world, before smartphones and airplanes and electricity transformed daily life. That light has been crossing the vast emptiness between stars ever since, neither speeding up nor slowing down, just faithfully carrying its message across the void. It passed through regions of space where no human eye could see it, where nothing marked its passage or acknowledged its existence in any way. And now finally, after all that time and distance, it arrives at our world and tells us something about a star that existed long before Earth formed. The delay is tiny compared to the star's lifetime, but it's still a reminder that astronomy always involves looking backward through time, seeing things not as they are, but as they were. Every star in the night sky is a messenger from the past, though some carry older news than others depending on their distance from us. The moon's light reaches us in just over a second, so when you look up at it, you're seeing it almost exactly as it is right now. The sun's light takes about 8 minutes to arrive, meaning the sun you see shining down is actually the sun as it existed 8 minutes ago. Some galaxies are so far away that their light has been traveling for millions or even billions of years before finally reaching our instruments to be studied. Methuselah's light doesn't come from the dawn of the universe itself, but the star that produced that light carries the dawn inside its chemistry somehow. Its light is recent in cosmic terms, only about 2 centuries old, but the star itself remembers a time before the Milky Way looked anything like it does today. That distinction matters more than it might seem at first, because it means we're not seeing Methuselah's birth or witnessing its formation in real time as it happens. We're seeing an old survivor that's close enough for us to examine carefully, a living fossil that carries physical evidence of conditions that existed billions of years ago. Distant, ancient galaxies show us the universe as it was long ago because their light took eons to arrive, giving us a direct view into the past. Methuselah does something different but equally valuable. It lets us study an ancient object that's still here in our cosmic neighborhood, close enough to measure with unusual precision. It's like the difference between finding an old photograph from someone's childhood and actually meeting an elderly person who lived through that time and still carries traces of it. Neither method tells us everything we might want to know, but together they paint a much richer picture than either could alone. The closeness of Methuselah relative to the vast scale of the galaxy is part of what makes it such a remarkable scientific treasure worth examining. Many of the oldest stars we know about are either extremely faint, impossibly distant, or tucked inside crowded globular clusters where measuring individual properties becomes frustratingly difficult. Methuselah, by contrast, is near enough and bright enough that astronomers can observe it in extraordinary detail, measuring its temperature, brightness, chemical composition, and motion with precision. It's not merely a symbol of ancient times or a vague representative of early stellar populations that we study for poetic reasons alone. It's a laboratory for cosmic history, a real object with measurable properties that can be compared against theoretical models and used to test our understanding. Sometimes the universe places its most important lessons right where we can reach them if we're patient and careful enough in our observations and interpretations. There's also something quietly profound about the fact that this star's nearby location allows us to peer so deeply into the past without looking far. We often imagine that studying the early universe requires powerful telescopes pointed at the most distant objects we can find, galaxies so far away their light has crossed most of cosmic history. That's certainly one way to look back in time, and it's given us remarkable insights into how the universe evolved and changed. But Methuselah offers a different path to the same destination. Instead of looking across vast distances at young galaxies billions of light years away, we look at a nearby ancient survivor. The light itself is recent, having traveled only a couple of centuries, but the object producing that light formed when the universe was still very young. It's the difference between reading an old letter sent from far away and sitting across from someone whose life spans most of recorded history, both valuable in their own ways. When astronomers first measured the distance to Methuselah with increasing precision, they weren't just adding a number to a catalog for completeness or satisfying some bureaucratic need. They were unlocking the star's true brightness, which in turn revealed where it sits on the great chart of stellar evolution and aging. Apparent brightness, the brightness we observe from Earth, can be deceiving because it depends on both the star's actual power and its distance from us. A dim-looking star might be genuinely faint and nearby, or it might be tremendously powerful but incredibly far away, and you can't tell which just by looking. Only when you know the distance can you calculate the star's true luminosity, its actual energy output, and compare it meaningfully to theoretical models. For Methuselah, that careful measurement of distance was crucial because it led directly to the age estimate that made the star famous and controversial. The Hubble Space Telescope, better known for its stunning images of colorful nebulae and distant galaxies, played a surprisingly important role in this story through work. Hubble's fine guidance sensors, instruments designed to measure tiny changes in position with extraordinary accuracy, helped refine Methuselah's distance by observing its parallax more precisely. Parallax is a beautifully simple concept. Hold up your finger in front of your face and look at it first with one eye, then the other. Your finger appears to jump against the background because your two eyes view it from slightly different positions, separated by the width of your face. Astronomers do essentially the same thing using Earth's orbit around the Sun, observing a nearby star from opposite sides of our yearly journey through space. The star appears to shift very slightly against the more distant background stars, and that tiny shift reveals how far away it is with remarkable accuracy. Once Hubble sharpened our knowledge of Methuselah's distance, astronomers could determine its true brightness with much greater confidence, placing it more accurately on the evolutionary path all stars follow. That improved placement allowed for a better age estimate, but it also revealed just how close that age came to the universe's own age. The refined numbers suggested Methuselah might be around 14.5 billion years old, give or take about 800 million years, while the universe itself clocks in at roughly 13.8 billion years old. At first glance, this looked like a serious problem, as if someone had discovered their grandmother was older than the planet she lived on, or found an artifact predating the civilization that created it. But the uncertainty range matters enormously here. With error bars included, the star's age doesn't truly contradict the universe's age. It just comes remarkably, uncomfortably, fascinatingly close to it. That narrow gap is where the real scientific work begins, where measurements must become even more precise, and assumptions must be examined with extraordinary care and skepticism. The earliest moments of cosmic history produced only the simplest building blocks, hydrogen and helium in overwhelming abundance, with barely a trace of anything heavier. These two elements alone couldn't build planets or bones or oceans or forests, couldn't give rise to the periodic table's rich complexity. Everything beyond them had to be manufactured inside stars, forged in nuclear furnaces where tremendous heat and pressure forced lighter atoms together. The first stars that ever existed worked with this sparse ingredient list, burning bright and hot with their uncomplicated fuel supply. They were probably massive and short-lived, dying violently after only millions of years rather than the billions that smaller stars enjoy today. When these early giants exploded or shed their outer layers, they scattered newly created elements into the surrounding space for recycling. This enriched gas would eventually collapse again under gravity's patient insistence, forming new stars from a slightly more complicated chemical recipe. Methuselah belongs to this second wave of creation, born from gas that had already been touched by stellar death, but not yet fully enriched. Its atmosphere contains far less iron than our sun does, perhaps only 1% of the solar abundance or even less. That scarcity immediately tells astronomers they're looking at something ancient, something that formed before the galaxy had cooked up much variety. The sun, by contrast, is a relative latecomer to the cosmic story, assembled from material that had been cycled through many generations. Our home star contains enough heavy elements to build rocky inner planets, gas giants, asteroid belts, and all the cosmic debris between. Methuselah's birth cloud lacked that richness, possessed only the barest seasoning of elements heavier than hydrogen and helium in its composition. This poverty is precisely what makes it precious to science, a window into conditions that no longer exist anywhere near us. In astronomy's peculiar terminology, everything heavier than helium gets lumped together under the catch-all label metals, which sounds odd to anyone familiar with chemistry. Carbon isn't a metal in the kitchen or the laboratory, nor is oxygen or nitrogen or any of the other gases we breathe. But astronomers use this simplified vocabulary because the Big Bang made almost exclusively hydrogen and helium, with only trace amounts of lithium. Everything else, from carbon to iron to gold to uranium, had to be created later through stellar processes and explosive events. So when astronomers say a star is metal poor, they mean it lacks this entire category of heavier elements in substantial quantities. The universe's first stars would have been essentially metal-free, composed almost entirely of primordial hydrogen and helium from the Big Bang's fireball. Methuselah isn't quite that pristine, but it's close enough to that original simplicity to reveal when and how the galaxy first started changing. The process by which stars create heavier elements is one of nature's most elegant pieces of alchemy, turning simple ingredients into complexity. Deep in a star's core, where temperatures soar into millions of degrees and pressures become almost unimaginable, hydrogen nuclei fuse together to form helium. This process releases tremendous energy, which is why stars shine in the first place, converting mass into light through Einstein's famous equation. As stars age and their cores grow hotter, they can begin fusing helium into carbon, then carbon into oxygen, and so forth. Massive stars climb even higher up the periodic table, manufacturing silicon, sulfur, calcium, and finally iron in their last desperate attempts at fusion. But iron is the end of the line because fusing it consumes energy rather than releasing it, so no star can survive that step. When a massive star reaches this crisis point, unable to generate outward pressure to balance gravity's inward crush, disaster follows swiftly and spectacularly. The core collapses in a fraction of a second, rebounding in a supernova explosion that briefly outshines entire galaxies before fading away. This violent death serves a creative purpose, though, because the explosion manufactures even heavier elements through rapid neutron capture and other exotic processes. It also hurls all those freshly made atoms out into space at tremendous speeds, seeding nearby gas clouds with chemical enrichment. Over billions of years, the cumulative effect of countless stellar deaths gradually increased the galaxy's heavy element content from nearly nothing to something substantial. Each new generation of stars inherited a richer mix than the one before, like a cosmic recipe that kept getting more interesting. Methuselah's chemical composition provides a snapshot of this gradual enrichment process, caught at a very early stage of its development overall. Its atmosphere reveals not just the absence of heavy elements, but also specific patterns in what little it does contain that astronomers find revealing. The ratio of different elements to each other tells a story about what kinds of earlier stars contributed to its birth cloud. For instance, some elements like oxygen and magnesium are produced primarily in massive stars that explode as supernovae relatively quickly after forming. Other elements like iron accumulate more slowly over time because they come partly from different sources with longer timescales for their production. If a star shows relatively high oxygen compared to iron, that suggests its gas was enriched mainly by massive stars early on. Methuselah's abundance pattern matches exactly this expectation for a very old star born when the galaxy was chemically young and simple. Scientists measure these abundances by examining starlight with instruments called spectrographs, which spread the light into its component wavelengths like a prism. Dark lines appear at specific wavelengths where atoms in the star's atmosphere have absorbed particular colors of light passing through them. Each element creates its own unique pattern of absorption lines, a fingerprint that reveals its presence and abundance in the stellar atmosphere. By carefully measuring the strength of these lines and comparing them to laboratory data and theoretical models, astronomers can determine what the star is made of. This technique, called spectroscopy, has revolutionized our understanding of stars by turning simple points of light into chemical laboratories we can study. For Methuselah, high-resolution spectroscopy reveals its metal-poor nature with remarkable precision, confirming its status as an ancient cosmic survivor from near the beginning. The concept of chemical evolution in galaxies might sound abstract, but it connects directly to our own existence in surprisingly intimate ways here. Every atom in your body heavier than hydrogen was made inside a star or during a stellar explosion at some point. The carbon in your cells, the oxygen you breathe, the calcium in your bones, the iron in your blood, all manufactured in stellar furnaces. When we look at a metal-poor star like Methuselah, we're seeing a universe that hadn't yet built the ingredients for planets or life. Its poverty in heavy elements represents a time before Earth was possible, before water could form in abundance, before rocks could solidify. The steady enrichment of the galaxy over billions of years was necessary preparation for the eventual emergence of worlds like ours that could support complexity. Methuselah formed during that preparatory phase, early enough that the cosmic kitchen was still largely bare and relatively simple in composition. This connection between stellar chemistry and the possibility of life gives ancient stars a poignant significance beyond their scientific value as data points. They remind us that the universe had to age and evolve before it could create conditions suitable for our existence anywhere. The first stars couldn't have planets like Earth around them because the necessary elements simply didn't exist in sufficient quantities anywhere yet. Only after multiple generations of stars had lived and died, enriching the galaxy bit by bit, could rocky planets form from dusty disks. Only then could water collect in oceans, atmospheres develop protective layers, and eventually life find its foothold in favorable conditions. In this sense, the history written in Methuselah's spectrum is also our history, the deep backstory of how the universe became capable of supporting us. Every metal-poor star we study helps us understand the path from simple to complex, from sterile to fertile, from barren to alive. The difference between Methuselah's composition and the Sun's composition spans billions of years of galactic evolution and countless stellar generations in between. Our Sun formed roughly 4.5 billion years ago from gas that had been thoroughly mixed and enriched by many prior cycles. By that time, the Milky Way had developed enough chemical complexity to allow planetary systems like ours to assemble from leftover material. Methuselah, forming perhaps 9 or 10 billion years earlier, drew from a much poorer pool of available elements in its original composition. Yet both stars tell part of the same long story, chapters separated by immense spans of time but connected through stellar nucleosynthesis. The ancient star shows us the beginning of that story, when heavy elements were scarce and precious, hard-won from the first generations. The Sun shows us a later chapter, when the galaxy had become rich enough to build worlds, life, and eventually curious observers. Between these 2 points lies the patient work of countless stars, each adding its contribution to the cosmic abundance we now take for granted. At first glance, the numbers seem to create an impossibility that shouldn't exist in any reasonable universe at all. Methuselah appeared to be roughly 14 billion years old, perhaps slightly more depending on which measurements you trusted most. The universe itself, according to our best cosmological models and observations, clocks in at approximately 13.8 billion years. You don't need an advanced degree in physics to spot the problem lurking in those two figures side by side. A star cannot be older than the space and time that contains it, any more than a building can predate its foundation. Yet here was Methuselah, sitting in Libra, seeming to break that fundamental rule with its ancient light and chemistry. Headlines inevitably seized on this apparent paradox because star older than universe makes for compelling copy that demands attention immediately. The real story, though, is more subtle and ultimately more interesting than a simple contradiction between observation and theory would allow. What we're really seeing here is science working exactly as it should, carefully and methodically examining unexpected results with patience. The age estimate from Methuselah came with uncertainty attached, a range of possible values rather than one precise number carved in stone. That range, about 800 million years in either direction, matters enormously when you're trying to determine cosmic chronology this precisely. If someone tells you their bus arrives at noon, plus or minus 20 minutes, you don't panic if it shows up early. The error bars aren't a weakness or failure in the measurement, but rather an honest acknowledgement of how difficult this work truly is. Astronomy at these scales and ages operates near the limits of what our instruments and methods can definitively resolve with confidence. Distance measurements played a crucial role in resolving the apparent age problem, because distance determines everything else we calculate about stars. If you don't know how far away something sits, you can't accurately determine its true brightness or energy output at all. Apparent brightness from Earth depends on both the star's actual luminosity and how far that light has traveled through space. A modest star nearby can look just as bright as a powerful star much farther away, which is why distance becomes critical. The Hubble Space Telescope's parallax measurements helped pin down Methuselah's distance with unprecedented precision, narrowing the uncertainty in that fundamental number substantially. With better distance came better luminosity, and with better luminosity came more accurate placement on models of stellar evolution and aging. Each improvement in one measurement cascades through all the others, gradually sharpening the picture we can construct from distant light alone. Chemical composition adds another layer of complexity to age determinations, particularly for metal-poor stars like Methuselah that formed so early. The amount of oxygen in a star's atmosphere affects its opacity, how easily light passes through its outer layers and escapes. Opacity influences the star's internal structure and temperature gradients, which in turn affect how quickly it evolves through different life stages. A small difference in assumed oxygen abundance can shift age estimates by several 100 million years in either direction easily enough. Measuring oxygen precisely in a faint, distant star is extraordinarily difficult, requiring high-resolution spectroscopy and sophisticated modeling of stellar atmospheres throughout. Different research teams using slightly different methods or assumptions about oxygen can arrive at ages that differ meaningfully from each other. This isn't sloppiness or incompetence, but rather the reality of extracting precise information from minimal photons across interstellar distances consistently. The evolutionary stage of the star also matters tremendously for determining how long it's been burning in the darkness of space. Stars spend most of their lives on what astronomers call the main sequence, steadily fusing hydrogen into helium in their cores. During this long, stable phase, they change relatively slowly, which makes pinpointing their exact age quite difficult from external observations alone. Methuselah has moved beyond that phase into what's called the subgiant branch, where hydrogen fusion has largely shifted to a shell. This transition happens as the core runs low on fuel and begins contracting while the outer layers expand slightly in response. The subgiant phase is much shorter than the main sequence, and stars change more rapidly during this time in observable ways. That makes subgiants particularly useful for age dating, because their properties at any moment depend more sensitively on how long they've existed. Methuselah's position on the subgiant branch helps constrain its age more tightly than if it were still burning hydrogen in its core. Different research teams over the years have published varying age estimates for Methuselah, each refining earlier work with new observations or models. Some studies in the early 2000s suggested ages as high as 16 billion years, which would have been genuinely problematic for cosmology. Later work incorporating better distances and improved stellar evolution models brought that estimate down toward 14 or 14.5 billion years. More recent analyses, particularly those carefully considering oxygen abundance and diffusion processes in the star's atmosphere, have pushed the age even lower. Current best estimates place Methuselah somewhere between 12 and 13.7 billion years old, comfortably younger than the universe itself, after all. The star remains extraordinarily ancient, among the oldest known objects we've ever studied in detail, but no longer impossibly so in conflict with cosmology. The resolution of this paradox demonstrates how science progresses through the gradual refinement of measurements, rather than dramatic revolutionary overthrows of everything. No one had to abandon the Big Bang theory or rewrite the laws of nuclear physics to explain Methuselah's apparent age issue. Instead, astronomers improved their distance measurements, refined their chemical analyses, and developed more sophisticated models of how metal-poor stars evolve over time. They carefully examined every assumption that went into the age calculation, testing which factors mattered most and which needed better constraints. The process took years and involved multiple research groups checking each other's work, sometimes agreeing and sometimes finding new sources of uncertainty. This collaborative, iterative approach might not make for exciting headlines, but it's how reliable knowledge actually gets built in science over decades of careful work. There's something reassuring about the fact that Methuselah didn't actually break the universe after all, just came remarkably close to it. The star formed very early in cosmic history, perhaps only a few 100 million years after the Big Bang, when conditions first allowed. It has survived for nearly the entire age of the universe, burning slowly and steadily while galaxies formed and evolved around it. Its chemistry preserves evidence of the young Milky Way, when heavy elements were still scarce in the galactic gas from which stars formed. All of this remains true and scientifically valuable whether the star is 13 billion or 14 billion years old, precisely and accurately. The specific number matters less than the broader story it tells about early stellar populations and chemical evolution in galaxies throughout time. The phrase, "within uncertainties," appears often in astronomical literature, and it carries more weight than casual readers might initially appreciate or understand. Science isn't about achieving perfect certainty in every measurement, which is impossible given the distances and complexities involved in studying the cosmos. It's about carefully quantifying what we know and what we don't know, being honest about the limits of our observations. Methuselah's age, like all stellar ages, comes with error bars that reflect various sources of uncertainty in the measurement and modeling. Those error bars overlap with the age of the universe when properly calculated and honestly reported, which means no genuine conflict exists. The star is old enough to be interesting and challenging, close enough to cosmic dawn to teach us about early times. That's what matters for advancing our understanding of how the universe evolved from simple to complex over billions of patient years. So Methuselah stands not as a paradox or impossibility, but as a testament to the precision required when probing deep time itself. It pushed astronomers to improve their measurements, refine their models, and think carefully about every assumption underlying their calculations of stellar properties. The star forced the field to confront the challenges of dating ancient objects with the accuracy needed to compare them against cosmology meaningfully. In doing so, it became one of the most thoroughly studied stars in the sky, its properties measured and remeasured repeatedly. The journey from impossibly old to appropriately ancient wasn't a failure of science, but rather a demonstration of how the process works. Patient observation and careful analysis eventually resolve apparent contradictions, not by abandoning inconvenient data, but by understanding it more deeply than before. The constellation Libra occupies a quiet corner of the celestial sphere, unremarkable to most who glance upward on clear evenings. It sits between Virgo and Scorpius, two far more dramatic neighbors that command attention with their brightness and distinctive patterns. Libra itself represents scales, an ancient symbol of balance and justice, though its stars form no obvious weighing device. The brightest members of this constellation barely reach naked-eye visibility under urban skies filled with artificial light pollution. Most casual stargazers pass through this region without pausing, their eyes drawn instead toward more conspicuous stellar arrangements nearby. Yet somewhere within these faint boundaries lies a point of light carrying secrets from the universe's earliest moments. Finding it requires more than just looking up. It demands intention, equipment, and the patience to search methodically through crowded fields. This is where Methuselah hides, not because it's trying to avoid detection, but simply because nature made it dim. The Henry Draper catalog assigned this star its designation HD 140283 over a century ago, during astronomy's great cataloging era. Henry Draper himself was an American physician who pioneered stellar photography and spectroscopy as an amateur astronomer in his spare time. After his death, his widow funded a massive project at Harvard College Observatory to classify stars by their spectral characteristics. Teams of skilled astronomers, many of them women whose contributions history initially overlooked, examined photographic plates through magnifying glasses tirelessly. They sorted hundreds of thousands of stars according to the patterns of dark lines appearing in their spectra, creating order. The HD catalog became one of astronomy's fundamental reference works, a phone book for the heavens, if you will. Each entry received a number based on its position in the sky, not its importance or brightness or any physical property. HD 140283 was simply one among many, a faint star that happened to fall within the survey's scope during observation runs. For decades, this numerical designation was all anyone needed, because HD 140283 seemed utterly ordinary by astronomical standards at first glance. It wasn't particularly bright, didn't show unusual variability, and belonged to no famous asterism that ancient cultures had named. The star was noted, catalogued, and largely forgotten except by specialists studying stellar motions in the solar neighborhood. Only gradually did its true significance emerge, as better observations revealed properties that set it apart from the crowd. Its high velocity became apparent first, showing that it moved through our region of the galaxy with unusual speed. Later spectroscopic studies revealed its extreme metal deficiency, marking it as a member of the old halo population rather than ordinary. These clues accumulated slowly, like pieces of a puzzle that only made sense once enough had been gathered together. By the time astronomers realized they had found something extraordinary, the star had been known for generations under its plain number. The nickname Methuselah arrived much later, after age estimates revealed just how ancient this faint point truly was in cosmic history. Naming a star after a biblical figure famous for extreme longevity felt appropriate once the numbers became clear to researchers. The name humanizes an otherwise impersonal catalog entry, making it easier to remember and discuss in both scientific papers and general conversation. It also captures something essential about the star's nature. This is an object that has simply refused to stop existing. While countless other stars formed, burned, and died around it, Methuselah kept shining with quiet persistence across epochs. The name stuck because it resonated with people who heard the story, providing an emotional anchor for abstract concepts. Still, professional astronomers continue using HD 140283 in their technical work, where precision and standardization matter more than evocative imagery. The two names coexist, formal and informal, serving different purposes in different contexts without conflict or confusion between them. Locating Methuselah in the actual night sky requires more effort than finding Orion's belt or the Big Dipper's familiar shape. Libra itself is visible from both hemispheres during certain seasons, reaching its highest point around midnight in late spring. The constellation lacks any truly bright guide stars to serve as obvious starting points for amateur observers with binoculars. You would need detailed star charts showing progressively fainter objects, allowing you to hop from one star to another systematically. Even with charts, distinguishing Methuselah from countless similar-looking faint stars in the same field requires checking positions carefully and repeatedly. Binoculars might show it as a tiny point indistinguishable from its neighbors, offering no hint of its remarkable nature. A small telescope improves matters somewhat, but the star still appears as nothing more than a dim speck against darkness. This modesty is part of what makes the discovery so striking. The most ancient object humans have ever studied looks utterly unremarkable. The distance of approximately 190 light-years places Methuselah firmly within our extended stellar neighborhood by galactic standards. This proximity is both a blessing and a reminder of how vast even nearby becomes when measured in interstellar terms. The light entering our telescopes tonight began its journey around the year 1830, when Earth's human population knew nothing of spectroscopy. It crossed empty space while empires rose and fell, while technology transformed society, while generations were born and lived and died. That light preserved information about the star's temperature, chemical composition, and motion in the patterns of wavelengths it carried forward. By the time it finally reaches our instruments in the present moment, the photons can be analyzed to reveal stories. Yet despite traveling for nearly 2 centuries at the universe's ultimate speed limit, the light has barely begun the journey. If Methuselah could see Earth in return, it would observe our world as it appeared around 1830, no satellites overhead yet. Methuselah moves through the Milky Way as a high-velocity star, its orbital path carrying it through our region at speeds that mark it as distinctly different from the Sun and its neighbors. The Sun and most nearby stars share the galaxy's general rotation, moving together like swimmers caught in the same broad current. Their motions are orderly and predictable, following circular paths around the galactic center at roughly 200 kilometers per second. Methuselah cuts through this orderly traffic on a different trajectory entirely, moving faster and at an angle that suggests deeper origins. Its velocity relative to the Sun reaches well over 200 kilometers per second, though that number varies depending on perspective and reference. This unusual motion caught astronomers' attention long before they understood the star's age, marking it as something worth studying carefully. High-velocity stars often belong to the galaxy's old halo population, objects that formed early and follow orbits shaped by ancient dynamics. They pass through the disk like travelers from another era, briefly visible before moving on through their long, elliptical paths. The halo itself is a vast, diffuse component of the Milky Way, surrounding the familiar disk like a dim, spherical aura. It contains old stars, ancient globular clusters, and the remnants of smaller galaxies that merged with ours billions of years ago. Unlike the disk, where new stars continue forming from gas clouds, the halo is largely quiescent and metal-poor today. Its stars formed when the galaxy was young and chemically simple, before multiple generations of stellar death had enriched the cosmos. They follow orbits that can carry them far above and below the galactic plane, sometimes plunging through the disk itself. Methuselah's motion and chemistry both suggest it belongs to this ancient population, though determining its exact origin remains challenging. It may have formed in the early Milky Way itself, or perhaps in a smaller system that was later absorbed. Either way, it carries information about conditions that existed before the galaxy settled into its current structure and appearance. The fact that something so significant requires equipment to see it all speaks to how deceptive appearances can be in astronomy. If we judged importance by brightness alone, Methuselah would rank somewhere below countless younger, more ordinary stars that happen to shine brighter. The brilliant stars of Orion are mostly massive, hot, and relatively young by cosmic standards, yet they dominate the winter sky. Methuselah has witnessed most of cosmic history unfold around it, yet remains invisible to unassisted human eyes under all but perfect conditions. This inversion of expectation, that the most ancient might also be the most modest, feels almost intentional, as if the universe enjoys irony. It reminds us that significance and visibility don't always align, that the most important stories sometimes require effort to uncover. The same principle applies elsewhere. The cosmic microwave background, carrying light from the universe's infancy, is far too faint for anyone to see. Black holes, among the most extreme objects imaginable, emit no light at all by definition, and darkness alone. So Methuselah sits in Libra, waiting patiently for anyone curious enough to seek it out with proper equipment and dedication. It asks nothing of casual observers who sweep past without pausing, content to remain unnoticed in its faint corner of sky. But for those who take the time to locate this modest point and understand what it represents, the experience carries weight. You're not just seeing a star, you're seeing an object that formed when the Milky Way was still assembling itself. The light entering your telescope left that star during Earth's 19th century, but the star itself remembers a time before our sun existed. Before planets could form from rocky material, before heavy elements had become common enough to build worlds, this faint spark was already burning. The contrast between its unremarkable appearance and its profound age creates a kind of cognitive dissonance that forces deeper consideration. Perhaps that's the real lesson here. The universe's greatest teachers don't always announce themselves loudly, but those who listen carefully discover truths worth learning. The methods astronomers use to measure a star's age feel almost impossibly delicate when you consider the distances and timescales involved here. You cannot simply count rings like a tree or check a birth certificate tucked away in some cosmic filing cabinet somewhere. The star itself offers no convenient timestamp, no little plaque announcing when it first ignited in the darkness of early space. Instead, scientists must gather clues from the light itself, from the star's motion and chemistry, from its position on theoretical charts. They compare what they observe against models of how stars evolve, looking for the best match between prediction and reality overall. It's detective work conducted across interstellar distances, using physics as the primary investigative tool for understanding. The process requires patience, precision, and a willingness to accept uncertainty as part of the answer rather than weakness. Distance serves as the foundation for almost every other measurement astronomers make about stars beyond our immediate solar neighborhood today. Without knowing how far away something sits, you cannot determine its true brightness or compare it meaningfully to theoretical expectations. Apparent brightness depends on both the star's actual power and how much that light has dimmed crossing space between us. A modest star nearby can appear just as bright as a tremendously powerful one much farther away in the sky. Parallax offers the most direct way to measure distance for nearby stars, using Earth's orbit as a baseline for triangulation. As our planet circles the Sun over 6 months, nearby stars appear to shift slightly against more distant background objects. The shift is tiny, measured in fractions of an arcsecond, but it reveals distance with remarkable accuracy when measured carefully. Hubble's instruments refined Methuselah's parallax, sharpening the distance estimate, and therefore everything that depends on it downstream in calculations. Once distance is known with confidence, astronomers can calculate the star's true luminosity, the actual energy it radiates into space each second. This number places the star on the Hertzsprung-Russell diagram, a fundamental chart organizing stars by temperature and brightness in patterns. The diagram reveals where stars sit in their life cycles, because evolutionary tracks show how objects of different masses change over time. Main sequence stars occupy a diagonal band where most stars spend their lives, steadily fusing hydrogen in their cores patiently. Giants and supergiants populate the upper right, swollen and bright, but relatively cool at their surfaces compared to smaller stars. White dwarfs cluster in the lower left, hot but dim because their small size limits total light output significantly. Methuselah sits in the subgiant region, having moved away from the main sequence as its core hydrogen supply diminished over time. Temperature measurements come from analyzing the star's spectrum, the rainbow of wavelengths it emits, and the dark lines carved through it. Hotter stars shine more toward blue wavelengths, while cooler ones favor red, creating a direct connection between color and temperature. But astronomers don't rely on simple color alone, which can be affected by dust and other complications in observations. They examine specific spectral lines created when atoms in the star's atmosphere absorb particular wavelengths passing through outer layers. The patterns of these lines reveal not just temperature, but also surface gravity and chemical composition in remarkable detail. For Methuselah, spectroscopy shows it's cooler than the Sun, but not dramatically so, consistent with a lower mass star. The real revelation comes from the strength of different element lines, particularly the weakness of iron lines indicating poverty. Chemical composition profoundly affects how astronomers model a star's internal structure and evolution over billions of years of existence. Elements heavier than hydrogen and helium increase opacity, making it harder for photons to escape from the interior outward. This affects temperature gradients, pressure balance, and ultimately how quickly the star burns through its fuel supply over time. A metal-poor star like Methuselah has lower opacity than the Sun, which changes its evolutionary track in subtle ways. The amount of oxygen matters particularly because oxygen is relatively abundant even in metal-poor stars compared to iron. Small changes in assumed oxygen abundance can shift age estimates by hundreds of millions of years in either direction. Measuring oxygen precisely requires identifying weak spectral lines and modeling how the star's atmosphere affects their appearance in observations. The subgiant phase makes Methuselah especially valuable for age determination because stars change more rapidly during this stage than before. During the main sequence, a star burns hydrogen steadily in its core with relatively little change in external properties. This long stability makes pinpointing exact age difficult, like trying to guess someone's age when they've looked similar for decades. Once the core hydrogen depletes, the star begins contracting and heating while fusion continues in a surrounding shell instead. The outer layers respond by expanding and brightening, moving the star away from the main sequence on the diagram. This transition happens relatively quickly compared to the preceding billions of years, making the star's position more sensitive to age. Methuselah's subgiant status lets astronomers narrow its age more tightly than if it were still burning hydrogen peacefully. Stellar evolution models provide the theoretical framework against which real observations get compared to extract meaningful age estimates from data. These models calculate how stars of different masses and compositions should change over time, step by step through their lives. They include nuclear reaction rates, energy transport through radiation and convection, and how gravity shapes the internal structure continuously. For metal-poor stars, the models must account for lower opacity and different mixing processes than occur in younger stars. Diffusion becomes important over billions of years as heavier elements slowly settle downward under gravity's patient pull over time. The surface composition we observe today may differ slightly from the original mixture when the star formed long ago. Models attempt to account for these subtle effects, though uncertainties remain about exactly how efficient different processes are. Different research groups have published varying age estimates for Methuselah over the years as measurements improved and models evolved. Early studies suggested ages as high as 16 billion years, which would have genuinely contradicted the universe's known age. Later work incorporating better distances from Hubble brought the estimate down toward 14 or 14.5 billion years. More recent analyses, especially those carefully considering oxygen abundance and other chemical details, have lowered it further toward 13 billion. Current best estimates place Methuselah somewhere between 12.5 and 13.7 billion years old, comfortably younger than the universe. The evolution of these estimates shows science working properly, refining conclusions as new information becomes available, rather than clinging stubbornly. The error bars attached to Methuselah's age represent honest acknowledgement of measurement limitations and modeling uncertainties throughout the determination process. Every input into the age calculation carries its own uncertainty that propagates through to the final result mathematically. Distance has uncertainty, temperature has uncertainty, chemical abundances have uncertainty, and models themselves contain assumptions that may prove imperfect. Rather than hiding these complications, astronomers quantify them carefully and report age as a range of plausible values. The phrase, "within uncertainties," appears frequently in technical papers, meaning the result is consistent with expectations given measurement precision. For Methuselah, the error bars overlap with the universe's age when calculated honestly and thoroughly without oversimplification. This removes the apparent paradox while preserving the star's status as extraordinarily ancient by any standard applied. So the oldest star we know in detail reveals its age not through one single measurement, but through careful synthesis of many. Distance, brightness, temperature, chemistry, evolutionary stage, and theoretical models all contribute pieces to the puzzle being assembled slowly. Each measurement refines the picture slightly, narrowing possibilities until the best age estimate emerges from the combined evidence available. The process took decades and involved multiple research teams checking each other's work, sometimes agreeing and sometimes finding new complications. What emerged is a star born very early in cosmic history, when the Milky Way was still young and simple. It has survived nearly the entire age of the universe, carrying chemical evidence of that early era in its light. The precision required to date such an ancient object within a few 100 million years is remarkable testimony to modern astronomy's capabilities. And the fact that we can do this at all, measuring the birthday of a star almost as old as time itself, suggests how far human curiosity has carried us into understanding our cosmic home with increasing confidence. The idea that ancient stars can serve as independent clocks testing the universe's age carries elegant symmetry worth appreciating in full. Cosmology measures the universe's age through several methods, including the cosmic microwave background radiation and galaxy expansion rates observed. These approaches look at the universe as a whole, treating it as a single evolving system since the Big Bang. Stellar astronomy measures individual stars or clusters, using nuclear physics and evolutionary models to determine how long they've existed. When these two completely different methods arrive at consistent answers, confidence grows that we're understanding something real about cosmic history. If the oldest stars were consistently older than the universe itself, that would signal a serious problem with either cosmology or stellar physics. But when ancient stars emerge slightly younger than the universe with proper uncertainties included, everything fits together reassuringly well. Methuselah became particularly important in this validation process because it's nearby, bright enough for detailed study, and metal poor enough to represent early times. Many ancient stars sit in distant globular clusters, where individual properties are harder to measure with precision and confidence. Others are too faint for high-resolution spectroscopy that reveals chemical details necessary for accurate age determination methods. Methuselah's proximity allows astronomers to measure its distance, brightness, temperature, and composition with exceptional precision compared to most ancient objects. Its subgiant status provides age sensitivity that main sequence stars lack due to their slower evolution over time. All these factors combined make it perhaps the single best individual star for testing whether stellar ages agree with cosmology. The early controversy over its seemingly impossible age focused attention on every assumption underlying the calculation being made. The resolution of that controversy demonstrates how science progresses through careful refinement rather than dramatic revolutions most of the time here. No one had to abandon fundamental physics or invent new cosmological models to explain Methuselah's initially troubling age estimate. Instead, astronomers improved distance measurements using Hubble, refined chemical analyses with better spectra, and developed more sophisticated stellar models. They examined diffusion, convection, nuclear reaction rates, and opacity in greater detail than previous generations could manage effectively. Each small improvement brought the age estimate down slightly until it no longer conflicted with the universe's known time frame. The process took years and involved multiple independent research groups checking calculations and assumptions thoroughly and repeatedly. This collaborative, iterative approach might lack drama, but builds reliable knowledge that withstands scrutiny over time successfully. Globular clusters provide another important way to constrain the universe's minimum age through studying their oldest remaining members carefully. These dense, spherical collections of hundreds of thousands of stars orbit in the Milky Way's halo, formed very early in galactic history. Because all stars in a cluster formed roughly simultaneously from the same gas cloud, they share a common age. The most massive members have long since evolved off the main sequence and died, while lower mass stars remain burning. The turn-off point where stars just begin leaving the main sequence reveals the cluster's age when compared to evolutionary models. Measurements of the oldest globular clusters consistently yield ages around 12 to 13 billion years, slightly younger than the universe. This independent confirmation that ancient stellar populations fit within cosmic timescales strengthens confidence in our overall picture of history. White dwarfs offer yet another stellar clock through their gradual cooling over billions of years after formation from dying stars. Once a star like the Sun exhausts its nuclear fuel, it sheds outer layers and leaves behind a hot, dense core. This remnant produces no new energy, slowly radiating away the heat accumulated during its previous active life gradually. By measuring the faintest, coolest white dwarfs in old clusters, astronomers can estimate how long they've been cooling down. This method is independent of main sequence evolution models, providing a valuable cross-check on cluster ages determined through other means. When white dwarf cooling ages agree with turn-off ages, confidence increases that both methods are capturing something real and accurate. The oldest white dwarfs found so far indicate cluster ages consistent with cosmological timelines, another piece of the puzzle. The convergence of multiple independent age indicators toward consistent values around 13 billion years feels reassuring in a field where certainty is always hard-won. No single method is perfect, each carrying its own assumptions and uncertainties that could potentially mislead researchers if not carefully examined. But when parallax distances, spectroscopic analyses, evolutionary models, globular cluster turnoffs, and white dwarf cooling all point towards similar conclusions, skepticism becomes harder to justify rationally. The odds that multiple unrelated errors would conspire to produce false agreement seem vanishingly small with proper statistical analysis. This is how science builds confidence in conclusions about things we cannot directly observe or manipulate in laboratories. The pattern of evidence from many directions becomes more compelling than any single measurement could ever be alone. Methuselah's role in this larger story is to anchor the ancient end of the stellar age scale with unusual precision. It's not the only old star we know, but it's perhaps the best-studied individual ancient star available for detailed examination. Its properties have been measured repeatedly by different teams using different instruments and methods over decades of accumulated observations. Each new study typically confirms previous results, while sometimes finding small corrections or improvements to previous estimates made earlier. This repeated validation gives confidence that we're not being fooled by systematic errors affecting all measurements in the same direction. The star has become a benchmark against which stellar evolution models are tested and refined for metal-poor populations overall. If models cannot reproduce Methuselah's observed properties at some reasonable age, that signals problems needing attention and resolution. The chemical composition of ancient stars like Methuselah also tests theories about how the first stars enriched the early universe. The amount of oxygen relative to iron in very old stars tells us about what kinds of early stellar deaths contributed to the enrichment process. Massive stars that explode as supernovae quickly after forming produce lots of oxygen and other alpha elements, but relatively less iron. If old stars show high oxygen to iron ratios, it suggests their birth gas was enriched mainly by these early massive stars. Methuselah's abundance pattern matches this expectation beautifully, showing the chemical signature of early galactic history preserved in its atmosphere today. This consistency between observation and theory strengthens our understanding of how the first generations of stars lived and died. So ancient stars serve as bridges between cosmology's large-scale view and nuclear physics' small-scale details in meaningful ways here. They connect the age of the universe determined from expansion rates to the ages of individual objects calculated from fusion. They link theories about early cosmic conditions to observable chemical patterns we can measure in stellar atmospheres today. They transform abstract concepts like the universe was chemically simple early on into concrete objects we can point telescopes toward. Methuselah represents this bridge particularly well, a nearby ancient survivor that lets us test whether everything fits together consistently. The fact that it does fit, within carefully estimated uncertainties, suggests our understanding of cosmic history is fundamentally sound, even if details remain to be refined through continued work and observation over coming decades and centuries ahead. Now we can let Methuselah's story settle into something quieter, a gentle companion for thoughts that need no particular destination tonight. This faint star in Libra has guided us through questions about time, chemistry, distance, and the universe's earliest moments. It has shown us how scientists work patiently through apparent contradictions, refining measurements until clarity emerges from complexity bit by bit. We've followed light that traveled 2 centuries to reach us, carrying information about an object that formed when the Milky Way was still assembling itself from smaller pieces. The numbers and methods might fade from memory, but perhaps something deeper remains, a sense of connection to deep time itself. Somewhere above you right now, though invisible to your eyes, Methuselah continues its ancient orbit through the galaxy's halo population. It doesn't know we study it, doesn't care about our attempts to measure its age down to the 100 million year mark. The star simply exists, burning hydrogen in a shell around its contracting helium core, gradually evolving toward its eventual red giant phase. Its light crosses space continuously, most of it passing Earth without being captured by any telescope or noticed by any observer. Occasionally, a photon finds its way into our instruments, gets spread into a spectrum, and contributes one tiny piece of data. From countless such pieces accumulated over decades, we've constructed the story you've heard tonight about this remarkable cosmic survivor. The universe has a way of hiding its most profound lessons in the most modest packages, requiring effort to discover meaning. Methuselah could have been bright and obvious, a beacon announcing its ancient nature to anyone who glanced upward casually. Instead, it's faint and easily overlooked, demanding careful search and patient observation to reveal its secrets over time. This seems fitting somehow, as if the cosmos rewards persistence and curiosity rather than casual glances at superficial appearances. The oldest surviving star we know in detail doesn't dominate the sky, but waits quietly for those willing to look closely. Its chemical poverty and heavy elements speaks to times before planets like Earth could form anywhere in the galaxy. Thinking about Methuselah's long existence can make our daily concerns feel simultaneously tiny and precious in contrasting ways here. This star has burned for most of cosmic history, while galaxies formed, evolved, and sometimes collided around it over eons. It witnessed the birth of our solar system from a distance, saw the sun ignite and Earth coalesce from debris. It was already ancient when the first life appeared on our planet, when dinosaurs roamed, when humans emerged to wonder. Our entire recorded history occupies only the tiniest fraction of 1% of Methuselah's lifetime so far accumulated. Yet that doesn't diminish our experience, but rather places it in context, showing the vast temporal landscape we briefly inhabit together. The fact that we can know any of this, that we've developed instruments and methods capable of dating ancient stars, speaks to something remarkable about consciousness and curiosity in the universe's story. We are made of atoms forged in stars like Methuselah's predecessors, scattered through space and eventually gathered into a world. On that world, some configurations of atoms became aware of their origins and started asking questions about where everything came from. We built telescopes to gather ancient starlight, spectrographs to spread it into rainbows, computers to model stellar evolution across billions of years. Through patient work spanning generations of astronomers, we've learned to read the universe's history in faint points of light barely visible. Perhaps there's a kind of poetry in the fact that one of the oldest things we can study is also one of the most difficult to notice without modern technology and knowledge. Methuselah doesn't advertise its significance, doesn't glow with impossible colors, or pulse with unusual rhythms to catch attention easily. It's just there, quietly burning hydrogen, moving through the galaxy on its ancient orbit, waiting for curious observers to ask questions. The answers it provides aren't simple, requiring sophisticated analysis and careful interpretation to extract meaning from minimal photons crossing vast distances. But the effort reveals something worth knowing, that the universe has a history, that stars remember that history through their chemistry and motion, that we can read those memories if we look carefully enough. If this quiet journey through deep time has brought you some measure of peace or perspective tonight, consider sharing it with others who might appreciate a gentle exploration of cosmic history before sleep. The universe isn't going anywhere soon, and neither is Methuselah, despite its great age accumulated over billions of years so far. Stories like this exist outside the urgency of deadlines and notifications, offering a different kind of companionship than most content provides today. They invite you to slow down, to think about time on scales that dwarf human experience, to find comfort in knowing we're all part of something much larger than individual lives allow us to grasp fully. So wherever you are listening from tonight, whatever time shows on your clock, whatever tomorrow holds, you can rest knowing that above you an ancient star continues its work of simply existing through time. It was there before you arrived, will remain long after you've gone, carrying forward the chemical memory of the early universe. Your brief awareness of it doesn't change the star, but perhaps it changes you slightly, adding one small thread of cosmic perspective. The oldest light we can study in detail has crossed 2 centuries to reach us, and in receiving it, we've connected momentarily with something that witnessed the galaxy's youth. That connection exists now, in this moment, between your awareness and a distant sun that's older than almost anything else we've ever examined closely. Sleep well tonight, knowing you've traveled far in imagination even while staying still in body throughout this gentle exploration here. Let Methuselah's patient example remind you that some things endure not through force or brilliance, but simply through quiet persistence over time. The universe rewards longevity, allowing modest stars to survive while more dramatic ones burn out quickly in cosmic terms. Perhaps there's wisdom in that pattern we can carry into our own much briefer lives, finding value in steadiness rather than intensity. Tomorrow will arrive soon enough with its own demands and distractions, but for now, let ancient starlight be your companion into rest. The cosmos has been here long before you and will continue long after, yet somehow your awareness of it matters, adding one more thread of understanding to the vast tapestry of existence, slowly being woven by all conscious observers throughout space and time together.